Hello, this is Rick Powers from Basic Statistics, doing an example of bootstrapping. So what I have here is a set of data, which is from a particular temperature measurement of days in February, the maximum temperature for each day. And so then with the analyzing of data, if we say, I want to be able to figure out what's going on with this data set, and then we say, well, I need to know if the population is bell-shaped. That would help me to be able to analyze this data. And let's say that we don't. We don't have an idea that this population would be bell-shaped. And we really don't know what's going on with this. And so we want to figure it out, but we don't have that information. So all we have is this sample. Now, in our textbook and in other situations, people say, well, let's look at this sample data set and let's see if it has any strangeness to it, or if it's bell-shaped, then maybe we can use it because it'll be relatively accurate as a sample. So then here in StatCrunch, I've already done this where I've made a box plot. And when I do a box plot of this sample data set, clearly it's skewed to the right. The right whisker is longer. And then if I do a dot plot for this, you can see it obviously also has outliers. So we're not supposed to be using this because both of these things, the fact that it has skewness and outliers, would say that the numbers that we get from this sample would not be a true reflection of what's actually in the population. So then we're like, well, what can we do? Well, what we're going to do is we're going to use bootstrapping to see what actually happens when we consider this data set from the bootstrapping perspective. So I'm going to delete both of these so that we can look at what bootstrapping is going to tell us. So the first thing we're going to talk about is just how to get there. So we're going to applets and we go to resampling bootstrap a statistic. And we're going to be working from the data table, the sample here. We have the maximum temperature in days of February. And we're going to choose to do the mean as a statistic. Now, when it talks about seeding for random data, that's just a computer science thing that says, how do we get some random choosing? How do we set up the computer to choose something randomly? And it doesn't matter really which one you use. Dynamic seeds are common. So then we hit compute. And what we have here then is we're going to be doing a bunch of resamples. We're going to take this sample of these numbers from February and we're going to resample them. So we're just going to go ahead and do this 1,000 times. So here we have 1,000 sets of data. Okay. The in this situation, there were 28 days in February. So we have all of these samples. Each sample here is a random collection of 28 values that came from this sample data set. So if I click on one of these, then it says, okay, we chose 28 numbers and we found the mean of those 28 numbers. And we did that 1,000 times. So there are 1,000 of these samples, these bootstrap samples that are out there. Now notice what happens, that we have a pretty decent bell-shaped looking thing. And we can do it even more times. So if we go up to 10,000, so you can see that it's kind of filled stuff in and it looks nicely bell-shaped. Okay, so even though the population may or may not be bell-shaped, we really don't know. By using bootstrapping, we've come up with a random distribution of sample statistics. So then we say, okay, now if these are what the samples look like, then the population you would expect would be in the center here, okay? But if we're going to talk about a 95% confidence interval, then we want to not just take the center of this, but we want to look at what happens with the tails. Now, what happens here in StatCrunch is that if we have a 95% confidence interval, then we have the lower 2.5% as the 2.5th percentile. And then for the upper 2.5, that the name for that is the 97.5th percentile. So what we have here for a confidence interval then would be 30.17 up to 37.82. So then this we would say, this is where we think the average of these maximum temperatures would be. Certainly sometimes we'll have lower maximum temperatures, sometimes we'll have higher, but the average for the month we're saying is somewhere between 30 and 38, basically. Now, if I go back to the actual data set here, and I say, what was true about this actual data set, then if I do my summary statistics for the column, and I'm just going to look at the mean and the standard deviation here, then, oops, I forgot to click the column. So this has a mean of 33.8, whereas here, this had a mean of 33.8. Okay, so it matches up, right? We know that that 33.8 is not accurate. So then where would the population mean actually be? Somewhere between 30.2 and 37.8. So that is our bootstrapped confidence interval. Now, if we say, would it be legitimate for us to use like the t statistic? Well, it's not really, because we're not going according to the rules of how it's been set up. But we don't have to worry, t statistic, whatever. We're using the bootstrapping to estimate the mean based on what we think a lot of samples would look like. And then we say, okay, the confidence interval will be where 95% of those samples are going to turn out to be. That gives us an interval which we think the population mean is most likely in there. So now we can take this and say, we can go beyond just doing the mean. We can actually bootstrap other things. And so what we're going to do is bootstrap the standard deviation. So I click on this, I compute it, and then again, if I do this 1,000 times, then what happened here? For each one of these samples, they were randomly chosen from the set. We had 28 numbers here, and we find the standard deviation of those things. So then we're going to just keep doing that. We're going to go up to 10,000 times. And once again, it looks relatively bell-shaped. It's not exactly symmetric. The standard deviation distribution is really complicated, and so we're not going to worry about exactly what that looks like. But we're going to say, look, it's most of the data is in the middle. We've got two tails. Is it really the normal distribution? It's not, but we don't need that. All we need is to find that 95% interval. So what we're seeing here, again, if we're doing the 95% interval, then we would say we have 6.94 on the bottom end, and we have 12.65 on the top end. And then we say, okay, what's the actual standard deviation? Oops, what's the actual standard deviation, it was 10.49. And we know that's not accurate because it's just a sample. So then we say, based on what we have from the bootstrapping, then it's somewhere between 6.9, 12.7. So again, we're not making any assumptions about what the population looks like. We're just saying, let's see what happens when we do this. Now, this data set worked out really nicely, gave us good information. Let's do another data set, a new data table, and we're just going to drop some numbers in here. 4, 14, 24, and 104. Okay, clearly just messed up numbers. If we go with this and we try the same thing, if we try to bootstrap this and we say, let's just use this variable 1, let's try bootstrapping the mean. And we do it 1,000 times. Oh, well, this is not working out very well. So let's keep going. 10,000 times. This is not nice. This is not bell-shaped. We're getting just a bunch of different little bell-shaped things that are happening. But this isn't good information. It's just a big clump of things in various places. Well, what if we were to have something like the standard deviation? What would that look like if we bootstrap that statistic? Well, it's really pretty strange. We keep going here 10,000 times. Yeah, this is just a mess. This is not telling us really anything about the standard deviation of a population. So if we have, when we do our bootstrapping method, if we have a distribution of these samples, which has globs of data or clusters, or just is obviously not bell-shaped, then we should not be using it. It's not useful. But the previous example that we had did definitely have a nice distribution, even when we were doing the standard deviation, which is not necessarily a nice thing to do or an easy thing to figure out. But this looks good. It looks relatively bell-shaped. And so we figure we can pretty much trust this kind of an analysis. So when you see something like this, then bootstrapping is working. And we're going to say that it's going to give us good information, which we need. All right. Best wishes on using bootstrapping.